Starting a new chapter today. As you can see, we're in now chapter 5, and today's lesson will be a basic probability lesson, hopefully some review involved. So you can see our title will be Calculating Probabilities. And so just to get us started, we'll do some defining of terms, and then we'll actually get into the math involved. So what is the meaning of probability? We could say that it's the mathematical process of assigning a numerical value to the likelihood of a certain event taking place. So the mathematical formula, if you will, the process for finding a probability is the total number of what we would call favorable outcomes divided by the total number of possible equally likely outcomes. So let's just put that equation into practice here with this first example. If we roll a standard six-sided die, or sometimes we use the word number cube, what is the theoretical probability that we will get a 1 or a 6? Well, let's just take each of these probabilities separately. So the probability that we will roll a 1, well, since there is a single number 1 on the cube, that would be called a favorable outcome, rolling a 1. And then the total number of possible equally likely outcomes would be 6, because there's a total of 6 numbers on the cube. Then, like in a similar manner, the likelihood that we're going to get a 6, well, there's one of those out of 6. And then it's pretty typical in probability calculations, if you do the probability of, I'll just call it like this, A or B, in this case, probability of 1 or 6, then that's a good clue that you're going to be adding these two separate probabilities together. So I'll finish it off this way. Okay, so I add these two together. 1 6 plus 1 6 is 2 6, and typically, like usual, if you have an opportunity to reduce, you need to go ahead and do that. So our final answer here would be 1 out of 3. Okay, here's another example. The second example, in a standard deck of cards, you probably already know this, but the cards are divided into 4 suits, 4 groups. And those 4 groups are called spades, hearts, diamonds, and clubs. And since there's 4 groups and there's the same number of cards in each group, there's 13 cards in each suit. 13 times 4 is 52. If I draw a card at random from the deck, what's the probability that I will draw an ace? Well, each one of these suits has an ace, so there's 4 total aces. And then there's a total of 52, so the favorable outcomes would be 4, and the total number of possible equally likely outcomes would be 52. And so now we just do the reducing. 4 over 52 would be 1 out of 13. And of course you could express these as percents or decimals. All right, number 3, if I draw a card at random from a standard deck, what's the probability that I will draw a diamond? Well, remember, there's 13 overall diamond cards. There's 13 cards in that suit. So we take the 13, that's the number of favorable that matches what we're looking for, 13 diamonds out of 52 total cards, and reduce, and we get 1 out of 4. So before we move on, let's just pause for a second and note some important facts about probability. As I mentioned just a minute ago, probability can be expressed as a fraction, a decimal, or a percent. We've just done reduced fractions, but I could I could have said this is 25%, or the decimal form 0.25. A probability must be between 0 and 1 inclusive. Okay, that just means 0 and 1 are they could be part of the answer, and all the numbers in between. So we can include 0 and 1, and then all the numbers between those. The probability of an event is 0 if and only if the event can never happen. Okay, so on the number cube, for example, what's the probability of rolling a 7? Well, there is no 7 on the cube, so that would be a 0 probability. The probability of an event is 1. In other words, that's another way of saying 100%. If and only if the event will always occur. So I could say, roll the number cube, what's the probability that I will get an odd or an even? Well, that's going to be 100% because all of the numbers are one of those two possibilities. Okay, pretty basic. I'm sure that's nothing new. Makes sense. So let's move on to distinguishing outcomes. We got to be careful when it comes to coming up basically with the denominator, the total number of equally likely possible outcomes. So this simple example will highlight the need to be careful. So we have this committee consisting of 3 members, Alan, Ben, and Jerry. We need to choose one of those 3 to be a representative, so they decide just to write their names on a piece of paper, and we'll assume that the pieces of paper are all the same size, so there's no one piece of paper that has a greater chance of getting chosen than the other 2. So what is the probability that we're going to choose Alan if we just choose randomly out of the basket? Well, there's one person named Alan, that would be the favorable, and there's 3 different names, 3 different pieces of paper in the hat. So we would have a 1 out of 3, or again, we could do that in percent form or decimal. Okay. Now let's change the scenario a little bit. Suppose that Jerry is replaced by another member whose name is Alan. Okay, so instead of Alan, Benny, and Jerry, we have 2 Allens, 2 different Allens. What's the probability that someone named Alan is chosen? So I may have had people in the past that would have said, well, now there's only 2 different people to choose from, so therefore I must have a denominator of 2. Well, that's not still the case. The case remains that there's still 3 different pieces of paper in the basket. Okay, so we still have 3 total possible equally likely outcomes. It's just that my numerator is going to change because now with 2 Allens I have double the opportunity or the possibility of choosing Alan versus Benny. Okay, so the number of favorable outcomes has changed because there's 2 Allens, then my numerator is 2. So this just highlights in a real simple way the need to be careful in distinguishing what the total number of possible equally likely outcomes would be. That's another way of saying the denominator. So we'll just go ahead and finish this thought. The error here is that these 2 outcomes are not equally likely. When we change the scenario, now because we have 2 Allens, we are twice as likely to draw Alan as we are Benny, so that changes the numerator, and the denominator is still the same because there's still 3 pieces of paper from which to choose. All right, so with that in mind, let's suppose I flip 2 identical coins. What is the probability that I get 2 heads? So I'll just call coin 1 and coin 2. This is a good little process to go through in these problems where you're using 2 or maybe 3 different items. Maybe it's 3 different number cubes that are being rolled. So we can go through all the possible scenarios, and that will lead us to easily calculate the answer to the probability. Okay, so let's just go through all the different possibilities of flipping 2 coins. All right, I could have a head on each. Okay, I will have maybe a head on coin 1 and tails on coin 2, or that could be switched. I could have tails on coin 1 and heads on coin 2, and the other possibility is that they're both tails. Okay, so here are the 4 different possibilities, and that becomes my total number of equally likely possible outcomes. That's the denominator. Well, the probability that I get 2 heads, well, there's only one of those possibilities out of the 4. So my answer here would be 1 out of 4. So this, again, just to reiterate our definition, favorable outcomes over total outcomes. Okay, here's another one. I got a 50-50 likelihood of getting through a traffic light without having to stop. This is a light that I go through on my way to work and then again on my way home. What's the probability of having to stop at this light at least once? So let's just make a similar little table here. I'll say to work and from work. Okay, so let's see all the possibilities. I'll just say going to work, maybe I had to stop in both, to and from. Or I could maybe stop going to, but not stop coming from. I may have not stopped going to, but then stopped coming from. And maybe I didn't stop either. So those are the 4 possible equally likely outcomes. That's the denominator. So letter A says, what's the probability of having to stop at least once? Well, here, here, and here. All of them except for the last. So there's 3 favorable outcomes out of a total of 4 total outcomes for letter A. So my answer would be 3/4. And then letter B, pretty obvious. What's the probability of not having to stop at all? That's the one possible favorable outcome to answer this question. There's only one possibility of that happen out of the total of 4. Okay, so we're moving right along. Probability of non-occurrence. So this kind of makes sense, I think, logically. The probability of something not happening is 1 or 100% minus the probability that it will. Okay, that's just summarizing that first little paragraph at the top. So let's just apply that in this example 6. We have several sections of English that we can choose from. Some of the English teachers I like and some I don't. I enroll in a section of English without knowing the teacher. There's a friend who has calculated the probability that I get a teacher that I like is 7 out of 17. Okay, so if that's the probability of getting a teacher you like, what's the probability of the non-occurrence, which would be getting a teacher that you don't like? So we just take 1 and we subtract from it the probability that I do get a teacher that I like. And just think of 1 as 17/17, and then minus 7 17ths would give you 10/17. And here's another one. You get emails. Some emails are bills and some are emails from friends. There is an email in your box. The probability that it is a bill is 15 out of 34. So you only have 2 options. Either it's a bill or it's from a friend. If the probability that it's a bill is 15/34, what's the probability that it's from a friend? Well, you just do 1 minus 15/34. So this is 34/34 minus 15/34, and it gets us our answer of 19/34. Okay, let's take a look at another example. We toss a pair of standard 6-sided number cubes. What's the probability that we get a 7? In other words, the 2 faces that show up would add up to equal 7. All right. So first of all, if you want the total number of possible equally likely outcomes, you can always do this. There's 2 number cubes, and each number cube has 6 sides. All right, so not 2 times 6. Each number cube has 6 sides. So to get that denominator in this case, you would just multiply these together, and so there's 36 total possible equally likely outcomes. Now, one of your problems on the assignment, you're going to be rolling 3 number cubes. Well, that just means to get that denominator, you're going to multiply 6 to the 3rd power, and that would be 216. So that'll be coming later, just to give you a heads up. So let's just think about all the ways that we could roll 2 cubes and end up with a 7. Okay, so you could have, well, let's just think about all the sums in general. Okay, we'll just start with 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, 5, 1 plus 6. Okay. There's 3 possibilities. If I just had 1 on, we'll just call that the left number cube, and then the right number cube changed. Okay, so these are all possibilities, but only one of those would give me a 7. Okay, so now let's just work through, what if this were a 2? 2 plus 1, 2 plus 2, 2 plus 3, 2 plus 4, 2 plus 5. 2 plus 6. So those are all the possibilities if the left cube was a 2. All right, so that would be 2 plus 5, which is 7. All right, so you can kind of get the idea. If every time we change this, just the left number, the face number, we will have another 6 possibilities, but only one of those, which would be 3 plus 4, would equal 7. Okay, then we do the 4, we change these to 4, and that would give us 4 plus 3. Okay, then we change it to 5, and 5 plus 2 would be the 1 out of those 6. That would give us the sum of 7. And then finally, if we change it to 6, we would have that 1. So I didn't list all of these out, but hopefully you can see that every time I do, I just change one of these by 1, I get another possibility of getting 7. Okay, so out of the 36 total possible equally likely outcomes, there's 1, 2, 3, 4, 5, 6 different ways of coming up with the sum of 7. And so we would reduce, and then if you did want to do percent form, it would be about 17%. Okay, well, what's the probability that we get anything but 7? Okay, well, if 1/6 is the probability of getting a 7, then going back to what we talked about a minute ago, the probability of non-occurrence, not getting 7, would be 1 minus the probability of getting a 7. So we just do the 1 minus 1/6, which is 5/6, and that's about 83%. Or you could think of it as 100% minus 17%. Okay, moving right along. Probability of disjunction. So what this involves is we have 2 events, A and B. Their disjunction is the event that either A or B occurs. Okay. We said earlier that if we do the probability of A or B, we would add. Okay, there it is. But sometimes we have this case where we have a probability of A or B, and then there's a probability that both A and B can occur. Okay, let's just take a look at what we mean by that. So this is just to kind of briefly summarize what's happening here. You've got a biology class, but you don't know yet who your professor is going to be. And typical in a college setting, you'll have a lecture professor, and then you might meet with him or her on Monday, Wednesday, Friday, and then on Tuesday, Thursday, you would go to a lab. And usually those lab professors, we'll call them instructors, are what we call graduate students, or TA, teacher assistants. They are also working on an advanced degree. Typically they're in that school working on their PhD, but while they're working on their own PhD, they'll teach a lab. Okay, so they're not a full-blown professor yet. So that's the scenario. So you want Mrs. Jones for grad assistant, and you want Professor Smith for the actual teaching lecturer. So the probability of getting Professor Jones, since there's 10 professors, it's a 1 out of 10 likelihood. He's 1 out of 10 total options. There's 5 grad assistants, and so the probability that you're going to get Miss Jones is 1 out of 5. All right, so this is the professor probability. Here's the grad assistant probability. But then you have the probability of getting both at the same time is 1 out of 50. So here's what I mean by you have 2 separate probabilities, but then there's a probability of both happening. And that's going to have to be subtracted. So here's what we mean by in the formula. The 1 out of 50 is the probability of A and B. You get Jones and Smith. So now we just do the math, and common denominator 1/10 is 5/50. 1/5 is 10/50, and then we subtract off the 1/50. So 14/50, which reduces to 7 out of 25, would be our answer. Okay, this is called a disjunction. Okay, the same thing on number 10, but we've increased the number of professor possibilities by 2. Okay, we've hired 2 new professors. So now the likelihood of getting Professor Smith is 1 out of 12. It's still 1 out of 5 to get the lab instructor Jones, because we still have the same number of grad assistants. But we still subtract off the probability of getting both, which becomes 1 out of 60 now. Okay, so again, common denominator, 1/12 is 5/60, 1/5 is 12/60, and then we subtract off the 1/60. So 17 minus 1 is 16/60. And then we reduce and we get 4/15. And in percent form, that would be about 27%. So it depends on what the problem is asking for. I just want you to know that if you did 4 divided by 15 in your calculator, that would be the decimal form, and then you would just slide the decimal 2 places to the right to change it to percent form. Okay, I think that does it for our notes. Oh, no, it doesn't. We got one more. Empirical probability. Empirical probability, we looked at this in Algebra 2, but we called it something different. We called it experimental probability, and that's actually the word that's going to go here. This is probability that's based on data that we've obtained from an experiment or past experience. Collecting data from the past will help us know the likelihood of something happening in the future. Okay, so here's an example. We're observing the intersection of 5th and Main. We want to know the probability that someone is going to go through that intersection and run a red light. So we put workers to gather information over a 5-week period. They actually counted 16,652 vehicles going through that intersection. So this would be our denominator, the total possible equally likely outcomes. But they only counted an actual 1432 that actually did run the red light. So based on that observation, that experiment, we are able to determine the probability that someone will run the red light, and it's based on this data So we would just go to percent form. So 1432 divided by 16,652, and in percent form that would be 8.60. Decimal form 2 places. Okay, now we're done with the notes. I think you are now ready to practice the assignment that has been given. And if there's anything I can do to help you with that assignment, if you have any questions, please let me know, and I will see you next time.